In this video, I'm going to demonstrate emulating a 6502 processor and an Apple II computer using C to program it. There's no machine code involved. So first of all, I'm going to actually demonstrate the actual emulator running on the computer. So here it is up and running. You can see the Apple II as it would boot up into BASIC, and it can run basic commands and things. And in my emulators, I can actually load a program by typing it in an automated fashion from a text file. So I'll do that just to display a sine wave as a graphics, as an example of a basic program running. You can see it goes through. It's got a couple of graphics modes. The Apple II. It's got a low res mode there, and it's got a high res mode. So this just switches between them and displays a sine wave on low res and high res. But I can press Control C to break into it. And then if I list the program, you see, because I'm still in graphics mode, you've only got a couple of lines of text at the bottom of the screen. But if I type text to go back into text mode, and you can see it shares, the text mode shares memory with the low-res graphics mode, so you can see kind of text representation of a low-res sine wave there on the screen. But if I type list, that'll scroll off and you can see the program. So that's the program which was running. But also every time I do an emulation, so in previous videos you'll see this Blitz game, just as a comparison between each of the emulators I'm doing. So it's always been Z80 computers that I've emulated up to this point. This is the first 6502 computer which I've decided to emulate, because I wanted to do some 6502 emulations, because I want to get all this stuff running on a Raspberry Pi Pico, hopefully. And so this is the Blitz program running in comparison with other computers in previous videos, and you can see the aircraft as it goes across the screen. It kind of does it in a kind of wavy effect, because on the Apple II the BASIC was quite primitive, because the computer was, I think, was considered the first commercially available home computer on the market, and so the BASIC wasn't particularly evolved that much, and so there's no way of locating the cursor on the screen with a BASIC command, or printing a string of characters at that position. So I have to poke the characters on to the display to animate them across the screen. So it kind of gives a bit of a wavy effect. I think that's probably because most other computers took their BASIC from Microsoft's BASIC, so they're pretty much very similar in effect. Microsoft BASIC came out for other computers after this, because, well, like I say, it was the first commercially available home computer. So I just go down until all this crashes into a building, and then I'll list the program. It's not a very big program, so I think it's less than 50 lines. So if I list the program there, so that's the Blitz program converted to run on an Apple II. So up until this point, I've just been doing emulators for Z80 computers. And now I've done an emulator for the 6502, which is for the Apple II computer. And just a quick explanation of the differences between the two processors. So on the left here, I've got the Z80 processor, and these are all the registers for the Z80 processor. And on the right, there's the 6502 processor, and it's only got a handful of registers in comparison. Some of the registers on the Z80 are for specific purposes, like the I register for interrupt vector table, and that provides an upper address of a vector table of jumps to interrupts, and the actual device which is interrupting the CPU will provide the lower part of that address, so it forms a 16-bit address, and whichever the 16-bit address is a pointer to the actual routine for that particular piece of hardware. So you can have loads of bits of hardware which have specific interrupts just for that hardware. So that's one of the modes of the interrupt modes of the Z80. It's got 3 interrupt modes. Another interrupt mode is just to call this RST38 function at the top of memory. And then the third one is the standard one which came from the 8080, which the actual interrupting device provides a Z80 instruction which needs to be executed, and those instructions will typically be one of these RST function calls, which is at the top of memory. And then of course you've got the non-maskable interrupts, which is here at address 66 which is a fixed address for non-maskable interrupts. Also, another specific register is dynamic RAM refresh. So on the Z80, if you had dynamic RAM in the system, which you would have done at the very early stages of the Z80 processor because it was a lot cheaper and easier to get hold of, it had circuitry within the CPU to actually handle the refresh cycles which are required in order to maintain contents of memory. 6502 doesn't have that, so you actually have to create a circuit with a 6502 computer to actually handle refreshing dynamic memory. And then it's got a stack pointer, which is a specific for like holding return values for calls to functions, or specific values that you just want to store in a quick place on the stack. And program counter is another specific specific register which you have to use for just the address where you're currently executing the code from. There's two index registers. Now they typically used for actually looking up values in tables from an offset, but they can be used as general purpose registers as well. Of course, the accumulator has a specific function which is to handle arithmetic and logic functions, and the flags as well. There's a register for holding the status of certain states of the CPU, and the other general purpose registers also have functions within block transfer and block input and output routines within the Z80 CPU, which makes it quite a versatile CPU. And then there's mirrors of these top registers as well, so you can switch quickly between one set of registers and another set of registers to do those specific purposes as well. As far as 6502 goes, you've got your accumulator where you do your arithmetic and logic stuff. You've also got XY registers which you can use as general purpose or for indexing values. You've got program counter, stack pointer. Now, the stack pointer is different on the 6502 because you only have one page of fixed area of memory that you can actually handle the stack on the 6502, and you can't change that. And so it's just at the top of memory underneath this 0 page. And again, this 0 page is fixed as well, and there's certain opcodes in the 6502 which only operate on this 0 page of memory. So these two areas are fixed, and you can use them for other things, but then it will get in the way of if you want to use some of the instructions, or it will reduce the amount of stuff you can, the amount of levels you can call into functions and stuff like that. And then there's processor status, which is basically the same as the flags on the Z80. So as far as interrupts on the 6502, you've got fixed vector table at the top of memory. So there's 6 memory addresses in pairs, because it's to make 16-bit addresses. So you've got non-maskable interrupt. You've got a reset vector. So when the CPU starts up, always reset. It gets the address from here as to where to start execution of the CPU. Whereas on the Z80, it always starts execution at address 0. And then you've got it's a software interrupt. It doubles up as a software interrupt and the maskable interrupt vector. So you don't have 3 modes of interrupt features on 6502. You only have the fixed one mode of feature, and they both have 64K of addressable memory space. So when emulating a computer using C, it goes through, this is the cycle which I use to actually do the emulation. So everything revolves around the CPU itself. So execution is immediately handed over to the CPU after the computer's been set up. So the first thing to do is set up the computer, and you set up memory map banks. So you can, if the CPU does, or if the computer does memory banking, then you have to set up how the banking is going to work at the start of the initialization. But some computers don't use memory banks, so you don't necessarily have to do that on some of the computers. There's memory callback as well. So using I/O on the CPU, you can either do memory mapped I/O, or on the Z80 you also have I/O specific instructions. So most computers that you come across for Z80 don't actually do memory mapped I/O, but some do. So I can, at the top, you register a callback for when a memory address is altered, then it will call back to the code which is actually emulating the computer and say, okay, this memory address has been altered, so you can do your memory mapped IO now. You also register a reset callback. So a lot of computers probably don't need this, but some of them do. So if you've got a sound chip, for example, or a video chip, you might want every time the CPU is reset to actually take advantage of that point to reset the sound chip and the video chip, or do other kind of initializations. You can also register a clock callback. Now this is on most of the emulated machines. I don't think I've done an emulation of a machine where I haven't used the clock callback. And basically this is where the emulation of the actual machine takes place. Normally it's for doing things like reading the keyboard and updating the video display. So a lot of computers have memory mapped video display, so you just read the video display from the memory and then plot it onto a window in Linux, say, or on the Pico microcontroller which I've used. Send it to the VGA display frame buffer, whatever needs to be done. So that's where the actual computer emulation actually takes place, the majority of it. On the Z80 you can also register for IO port callbacks. Because the Z80 has dedicated instructions for doing input and output, for a particular port you can register that as a particular callback, and when you're emulating the actual computer itself you can say, okay, for the sound chip call back this routine, for the video chip call back this routine, and they can be separate routines. It makes it nice and versatile for doing Z80 emulation. And then I do the reset of the computer, whatever happened, and the CPU, whatever needs to be done for resetting the CPU is done here, and it also calls back the virtual machine, or the emulated machine, and it will call back the reset routine for that, so the emulated machine can do whatever reset stuff it needs to do, and it comes back to here and continues down the process. Now in the actual, this is the actual loop of the emulation, so it keeps going round and round this loop. First of all, it checks to see if a reset's occurred, because the user might actually do a reset through a menu option on the emulator, and if a reset's occurred then it will jump back to here, and it will do the reset callback again, and that can happen at any time. Then it will check to see if non-maskable interrupts occurred, and if it has, on the Z80 processor, it will call this routine at address 66. And then it checks to see if a maskable interrupt occurred, and in the particular mode it will call this function at 38, or it might do one of the other modes of interrupt, like looking at the next instruction on the bus and executing that, or looking up the interrupt vector table where to actually do the interrupt call from. Next it will do the clock callback. So this is the emulation of the actual machine itself, and it says to the machine, okay, do whatever hardware stuff you need to do for this particular clock cycle. So it'll pass through like the clock cycle number which is occurring, and then the actual emulation of the hardware can say, okay, so many clock cycles have passed, so I need to do this, or I need to do that, or I need to stop doing this if I started doing something. And then it just goes through all of the opcodes in the CPU. I've got a switch statement which I do, and I just say, okay, what's the opcode being executed, and it will only execute whichever opcode has been chosen. So it might be a NOP operation, and if it was NOP, it'll do that, and it'll recycle back to the top of here and go through all of these things again, and it'll say what's the next instruction, and it might be an input instruction this time. It'll do this, and because it's an input instruction, if someone's registered on the particular port which is in this particular instruction given by the register C, so they give it a port number, if that port number has been registered for a callback, it will call that specific function in the emulated computer, and then it will return back to here and continue around the loop again, get the next instruction. Maybe it's a load instruction, and again, because it's affecting memory, this one, it will do a memory callback if it's been registered, if a function has been registered for a callback there. But it'll keep going around, it will just do whatever opcodes come up to actually emulate the machine, and that's just how the emulation works for the Z80. So the actual emulation cycle for 6502 is very similar to the Z80 cycle. even though the CPUs are quite significantly different in the way that they're constructed and the features of them, the process itself is actually very similar. So first of all, it sets up memory banks for the emulation if required. Not all computers require memory bank switching. Then you can register a memory callback. So the 6502 doesn't have specific I/O instructions in the opcodes, so you can't have I/O ports like you can on the Z80. Any I/O that occurs has to happen through memory addresses. So you specifically allocate a memory address for the hardware to talk to, and you can read that memory address, and you're not reading memory, you're reading what the information the hardware has given you. And the same with if you write to specific memory addresses which have been allocated for hardware, you're not writing to memory, you're writing to the hardware itself. So after that, you can register a reset callback. So again, like the Z80 in emulating computers, you might want sound chips to be reset when a reset occurs for the actual CPU itself. And register the clock callback. So for every clock cycle, it will call this callback, and this is where the emulation of the actual hardware, the machine itself, goes on. Then reset of the CPU occurs. It will call the reset callback for the hardware if one's been defined. And the actual start address for the 6502, it will get from the address FFFC and FFFD. So this is a pointer to an address where it's to start from. So it won't jump to this address, it will read the memory from this address and the next address. That will be the address at which it starts at. So when it comes around the actual execution cycle, which it does one after another after another, first thing it does is it checks for a reset, and if a reset has occurred, then it will redo this reset here, call the user's reset routine, and it will look up again the address in here as to where to start execution from. It will check to see if a non-maskable interrupt's occurred. If it has, then the actual address that it needs to jump to is stored at this address. So again, this is a pointer to where the actual code is for the non-maskable interrupt. It checks to see if a maskable interrupt's occurred, and if it has, then it will jump to wherever this address points to. And that's the only type of interrupt you can have on here. You can't have the other types of interrupts which occurred on a Z80 CPU. So you had 3 different types of interrupts there, but there's only this particular interrupt for maskable interrupts on the 6502. Next, it will do a clock callback if one's been defined, which for most, or probably pretty much all emulations of computers will have a callback for this, and this will do reading the keyboard or outputting to display or anything else which needs to be handled and monitored. And then it will start executing the opcode for this particular cycle, and if there's not an op instruction, it will do a nop, which is no operation, and it come back around to the top again and look for whatever the next instruction is. Then maybe it's a transfer A to X, and it'll do that, and it'll come around to the top, increment the program counter, and the next one might be a store a 0 pointer indexed with the X register. And because this is affecting memory, if that memory is registered as being hardware, they do a memory callback, and the actual emulator itself can handle any memory mapped hardware that might need to be serviced at that point, and that's how it does its I/O. So the configuration file for emulating 6502 computers is the same as the configuration file I would use for the Z80 computers that I've emulated, because it all runs off the same libraries. And at the top, I just define the name of the emulation, how fast the clock is which is being emulated. I think I probably still have to configure that a bit better. I'm not sure if I've got the speed quite right for 6502. Then it configures how wide and tall the display is in pixels and characters, and how big it needs to be for the actual window on, say, Linux. It defines some default colors for foreground and background. For when the actual automatic typing of programs in by selected text file on the emulator, These are the delays for the actual key presses to make sure each key is recognized. It defines the color palette for the Apple II computer, the graphics that are displayed. And then the character set of the Apple II is defined here. And this character set is mainly so that when I'm debugging on my debug window, where it displays ROM addresses, things that are typed that are ASCII in the ROM, the sharp as actual like words, so that it makes it a bit easier to see actually what characters are being displayed. Then it defines the keyboard matrix for the Apple II computer. And for that, those values up there, the scan codes are placed into what happens when a key is pressed. So for each key on a keyboard, I define what scan code for the Apple II computer is required when that key is pressed. So if a B is pressed in the hardware, it will return the value 1E2 so that can be resolved with the Apple II ROM and be an appropriate key press. And then here I've just got lookups. So again, this is for the text entry of selecting a text file and it automatically typing stuff. It converts what it might find in a text file into whatever character it actually requires to be received. So here you can see everything's being converted to lowercase letters because there's no uppercase and lowercase distinction. And then just at the bottom, this is for debugging, and it's things like error codes and just some information about where functions are within the actual Apple II ROM, so it makes debugging a bit easier. So the actual emulation of the Apple II computer is handled in this source code file. At the top, I just have some global variables, and I say like get these variables from an external source, and that's just an interface with the libraries for my emulation. And it uses the same libraries as the Z80 emulations as well. Here I've got specifically for the Apple II display mode, because the Apple II uses color artifacts in order to create its colors. In high res mode, I've emulated the artifacts that you should get when actually it plots pixels on the screen, so it gives the unusual sort of color scheme. And this is where I enter the emulation itself. So if I'm just writing a Linux program, it calls into this main function. But if it's in the microcontroller, then I have multiple entry points for each different emulator which I'm emulating. So I might be emulating Spectrum, Z80, and so rather than, you can't just have one single, you can't have three main functions for each of those emulators, you have to call them different things. So that's why I've got this separate entry point here. That's when I'm doing microcontroller stuff. So at the top I just define what config file I'm using. I initialize the display. In this case, it will initialize a Linux display. When I actually run it on the microcontroller, this function call will handle whatever display needs to be set up. I initialize beep hardware because it likes the Spectrum. It's got like a little speaker which can beep. So I initialize the same hardware as I would do on the ZX Spectrum there. I initialize the CPU. In this case, it's 6502. In all the other cases up to this point, it's been a Z80. It loads the ROM file into memory. And what I'm doing here is I'm loading it into the top of memory. So however big the ROM file is that it needs to load, it loads it from the top of memory down to however far down it needs to load it. There are other ROMs which I've taken into account for as well, which I can also load. This is the character ROM, so the actual display itself in text mode uses a character ROM, so I'm loading that into above the top of memory. So this is the 64K boundary, so it goes above the memory of the computer, above the 64K. I'm setting an area of memory to write protect, So it uses memory mapped I/O, like say for the 6502, and I'm making this particular part of memory read only. That way, the computer will think that the hardware doesn't exist in that area of memory, so it won't try and use hardware there. I call reset for the I register a reset callback so that I can get a callback when the CPU resets. I register a memory callback because all the hardware for the 6502 is memory mapped, so I'm going to need a callback for whenever hardware is being accessed. And I have the clock callback, which does the rest of the actual emulation of the Apple II computer. So I just do a display refresh just to make sure the display is updated before I start the emulation, just to make sure it's clear and everything. And then I start the execution of the 6502 CPU, and it will then go immediately to wherever it needs to go to for the reset vector and start execution. At this point it's come back out, so if I'm terminating the emulation, it's coming out here and it's just terminating the beep hardware, terminating 652 CPU, quitting the display, closing the window, and then coming out of the actual program itself. And here is the actual callback for the reset. So for the Apple II, when it does a reset, what it does is a memory randomize. I've never done this on a previous emulation, but on the Apple II computer, when you start them up, they have random stuff on the display. It's to do with the way that the actual display hardware is actually configured. So just to emulate that and have it consistent with how the hardware would actually do it, I just randomize what's in memory completely. And then I clear the memory at the memory mapped I/O for the Apple II computer, so that the Apple II starts off with hardware which looks like it's been reset. This is where I do memory map callback. So this is all of the I/O operations for the Apple II I do in this function here. So whenever memory gets read or written to, it will call this and say, it will say to the emulator, is this actually something you want to handle as part of hardware being accessed? And so in here I can switch on the address, decide if it's an address which is actually memory mapped hardware, and for this top bit it's doing keyboard hardware operations here. And it's doing speaker operations here, so you can see I'm setting the beep high or beep speaker low for making the beep. For doing cassette output, it does there, so it just creates, if someone does a save, it should create the audio on the speaker for it saving. And then there's hardware addresses for switching the display mode, and so I'm doing that here. So if the actual program itself changes a memory address, say I'm changing the graphics mode from text to low res graphics or to high res graphics, then it will do that operation here. And that's all of the hardware which I've supported so far. I think there's more hardware which really needs to be supported as well. And this is the main emulation function here. So every clock cycle it will call this function, and it's going to update the display frame on the actual Linux window every 50 Hertz, 50 times a second. So while it's doing that, every 50 times a second, it will also handle key presses. And this is how it handles key presses. Now, if you look at all of my other emulations for the Z80 computers, none of them are as complex as this for handling key presses, because it's got its own hardware keyboard. So most computers have like a matrix, which the computer just scans the matrix and it knows what the actual key press is directly from just like a couple of bytes. But this one has a specific way the keyboard works, and it actually talks to the keyboard through 2 memory addresses, or it might be a few more than 2 memory addresses, but you actually have to handle when memory's changed and how it's changed, and it's quite a complex process under this. But the code up to there handles the keyboard presses. Because the Apple II computer, I think, operates more like a terminal than it does a computer sort of thing. and then it updates the display of the frame, the display frame, and it can handle it updates in text mode or in mixed mode, and it'll update the low res graphics there. So this is like how it updates low res graphics. It does the high res graphics display in here if it's in high res graphics mode. Well, it's actually probably in mixed mode, so it will display low res or high res at the top of the screen. Then down the bottom of the screen it'll display text, or it will just display the whole screen as text. But it actually handles updating the display by choosing how much of the display it's going to do low res, how much the display is going to display high res, and how much the display it's going to display as text. And again, because that's specific hardware for the Apple II, it's fairly complex in the way it handles the display, whereas most computers of that era only have really one or two graphics modes and not much more, whereas this one's got quite a complex support for its graphics. And that's the emulation.